Hi guys, right now today we're going to have a look in your booklets and we're going to have a look at conditional probability. You most probably have not seen this before in year 9 or 10. You may have glimpsed it a little bit, but most of you would not have seen this. So it's new. New is okay, new is just different, and we'll go with it and we'll have a look at how we go. So I'm going to do the work for this, which will be 10G over on our 10G page in the OneNote that says conditional probability. I'll still work through your examples though. So conditional probability. So what is that and how does it look? So we write this as a conditional probabilities. We're going to be working out the probability P, if I can get my pen to work today. So we're going to be working out our probability, or P, of some event A given B. So we want to work out the probability of A, given that we have other information that we can find useful to work out that probability. So we read this as A given B, or the probability of A given B. So we're still working out what the probability of A is. There's just this other information that we've found out that is, we're going to call B, that we're going to bring into that question as well to help us work out the answer. So there's a little formula that we use to work out this. And the formula that we use to work out the probability of A given B is the probability of A and B, or A intersection B, over the probability of B. So we're going to have a look at some questions working out what the probability of A and B is and the probability of B is, and seeing how that can help us work out what A given B is. And here's our first example from your booklet. Let's read it. A card is drawn at random from a normal pack of 52 cards. Find the probability that it is a 9, 10, Jack, or Queen. And there's a few provisos down the bottom. Let's look at A. So it says in part A, if nothing more is known. So we don't have any given B part. We're going to do it as if we were doing it in the last couple of exercises. We're going to be finding the probability of the card selected being a 9, a 10, a Jack, or a Queen. So the probability of a 9, a 10, a Jack, or a Queen, let's have a think. We've got 52 cards. There are 4 9s, 4 10s, 4 Jacks, and 4 Queens in that card pack. That will give us 16 cards all up. 16 out of 52 breaks down to 4 out of 13, which is the answer that we have for part A. Okay, let's now have a look at part B. So we're still finding the probability that it is a 9, a 10, a Jack, or a Queen, but part B says it is known to be a court card. So that's our extra information. That's our part B. That's the given. That's our proviso bit. So, known to be a court card. Well, how many court cards are there out of 52? We've got a Jack, a King, or a Queen in each of our suites. That's 3 cards. We've got spades, clubs, diamonds, and hearts. So 4 times 3 is 12. So 12 of those cards fall into the given B part. Let's have a look at the first part. Oops. So to find our A given B, we need to look at our A and B. So what happens in our A and our part B? So let's think what's happening. We to start with, we're looking at finding the probability that it is a 9, a 10, a Jack, or a Queen. But it is known to be a court card. So the intersection of court card and 9, 10, Jack, or Queen is just going to be Jack or Queen. Okay, so let's think what's happening there again. Let's work it out. We're looking at the A and B, or the number of elements in our A and B. We've got A being 9, 10, Jack, or Queen, and B being that is a court card. So we need to find what's in both of those, and that would be the jack or the queen. So how many jacks or queens are there in our set of cards? Well, there's in each of the suites, we've got 2. There's 4 lots of 2, so we've got 8. So our probability of A, which is the probability of finding a 9, 10 jack or queen, given that it is a court card. So if you need to write court card in there, that might help you. And the A, that it is a 9, 10 jack or queen, is our A and B, which we've worked out as 8, our B, which we've worked out as 12, and that breaks down to 2/3. Let's have a look at C. So we're still finding the probability in part C that it is a 9, a 10, a jack, or a queen. So we can write that A, that it is a 9, a 10, a jack, or a queen. Oops. But our part B is, sorry, my pen's playing up in a big way today. And our part B, or our proviso, or the given part is, part C tells us it is known to be an 8 or a 10. Okay, so we'll say that again. So we're finding the probability of A given B. So we're finding the probability of a 9, 10, jack or queen, given that we know it is an 8 or a 10. So let's look at B first. An 8 or a 10. How many 8s or 10s are there in a pack of cards? Well, let's think. So in each of our 4 suites of cards, there are 1 8 and 1 10, and we've got 4 lots of those 2, so we have 8. So that's where that 8 comes from there. Now, A and B. What is in A and in B? Let's have a think of that. A and B. The only thing in both of them is the 10. Okay, how many 10s are there in our pack of cards? There are 4. So it's fairly easy when you write it down and think of it like that. So the probability of A given B, or the probability that we select out of our 52 cards, a 9, a 10, a jack, or a queen, given that it is an 8 or a 10, and using our formula, A and B over B, we go back and we find, well, what did we work out for A and B? That was 4. What did we work out for B? It was 8, so we work out a half as our answer. Okay? Okay, one part of that question to go, and that is part D. Okay, so we are still finding the probability that it is a 9, 10, jack or queen, but it is given, or it is known, not to be a 2, 3, 4, or 5. Okay, so let's look at what I've written down here for that one. So it is known not to be a 2, 3, 4, or 5, but what is it known to be? So it could be an ace, a 6, a 7, an 8, a 9, a 10, a jack, a king, or a queen. So that's everything else in a suite of cards other than a 2, 3, 4, or 5. Okay, so let's look what our parts are going to be. Our B is the given. Okay, so that's our given. So our given is that it can be an ace, a 6, a 7, an 8, a 9, a 10, a jack, a king, or a queen. So how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 cards, 4 suites. 9 times 4 is 36. Okay, we now need to think of what's happening at A and B, or the intersection between A and B. Okay, remember, B is our given part up here, where I've written given, and A was originally what we were trying to find out. So A is our probability of finding the 9, the 10, the jack, or the queen. So we might write that up there. So A is the 9, the 10, the jack, or the queen. So the intersection of A and B is what's in both A and in B. And let's have a look at that. Well, we've got a 9, a 10, a jack, or queen as our A, and all of those are in our B. So there's 4 of them in the intersection in each suite. Okay, remember we've still got to think of the spades, the clubs, the diamonds, and the hearts, because there's each one of those 9, 10, jack, and queen in each of those 4 sweets. So we've worked out that they're in the intersection. Okay, there's 4 different cards, 4 different sweets. So 4 times 4 is 16. So our A and B gives us 16 cards. So let's think back to our formula. The probability of A given B is A and B over B. A and B we've worked out to be 16. Our B we worked out to be 36. So our answer is 4 9s. So you might need to go back and have a look at that and have a little bit of think of that yourself and see if you can pull out each of the A and B's and the B's for that question. And we'll go and have a look at the next one. So this is the next example that I would like to have a look at. It says, in a certain population, 35% of people have blue eyes, 15% have blonde hair, and 10% have blue eyes and blonde hair. So I've written that down here, okay? So the probability of picking a blue-eyed person would be 0.35, so we've just changed our percentage to a decimal. The probability of blonde hair is 0.15, and the probability of blonde hair and blue eyes is 0.1. The question says, a person is chosen from this population at random. Part A, we want to find the probability that they have blonde hair given that they have blue eyes. So what we're trying to find out for part A is this little formula here, the probability that they have blonde hair given that they have blue eyes. So what we need to do is think of what our formula up here is telling us, and I'm just going to write it in terms of blonde hair and blue eyes. So it's going to be the probability of the intersection of blonde hair and blue eyes over the probability of just blue eyes. So if we have a look at our formula over here, the probability of blonde hair and blue eyes is 0.1, and the probability of blue eyes is 0.35. So if we divide that, we get a 0.29. So it's fairly easy when you're thinking about what's happening here. And we've had a nice question, I guess, that's given us this and already. Now, part B says, find the probability that they have blue eyes given that they have blonde hair. So the probability that they have blue eyes given that they have blonde hair. Well, let's have a look at that one. It's going to be the probability of blue eyes and blonde hair again over the probability of blonde hair. So a little bit different to the first one, but not too much. We've got our numbers over here. Top one, probability of blonde hair and blue eyes is 0.1 divided by the probability of blonde hair, which we had as 0.15. So our answer, 0.6 repeater, but I'd prefer that you write that as 2/3. That one wasn't too bad. There's a little note I've put down the bottom here though. Now, we'll have a look at this in a second, but we might actually come back to this point in a second, but our information there shows us that these events are not independent. And I guess we can think of them as they've got blue eyes and blonde hair happening together, but I'll just jump back to this in a second when we go over a couple of the other notes. Here are a couple of other notes that are in our one note that talks about independent events. 2 events A and B are called independent if the probability of A is not affected by knowing whether or not the probability of B has occurred. So if we're saying that we want to figure out the probability of A given B is equal to just the probability of A, that would mean that, okay, we don't care what happens with B. B doesn't affect A. B doesn't come into play, okay? Another way to look at it, to check for independence, is if we're working out the probability of A, B, that would be the probability of A times the probability of B. And that would allow us to check for independence. And that's what I was just talking about with the last question. I've written that the probability of blonde hair and blue eyes is not equal to the probability of those together. And that should be a times in there, not a little plus. I'm just going to change that. That should be a multiplication. There we go. So the probability of blonde hair and blue eyes does not equal the probability of blonde hair times the probability of blue eyes. We know the blonde hair and blue eyes probability is 0.1. We know each of these, and when we times them together, they are not equal. So we would say these events are not independent. And that's a way that we can test for that.